Forget the audio myths and overhyped marketing. If you want to properly modify an amplifier, you need to understand the basic material science, not just the capacitance label. Welcome to Rty DIYaudio. Today, we are skipping the guesswork and breaking down the practical rules of capacitor upgrades. Let's get started. Disclaimer. Before we unpack the blueprint, a strict safety notice. DIY audio modifications involve high voltages and active power supplies that carry serious risks of electrical shock or hardware damage. The circuit engineering logic shared in this masterclass is for educational purposes only. You proceed entirely at your own risk. Rty DIYaudio assumes zero liability for any component failure or technical errors on your workbench. Always prioritize electrical safety and verify your circuit layout before you solder.
Agenda. Here is our volume masterclass course outline, focusing on the core technical blueprint from start to finish. We begin with Chapter 1, breaking down why your sound profile changes based on the 4 factors. Chapter 2 unlocks material science secrets, comparing standard components directly against boutique engineering. Chapter 3 targets node priority, revealing which capacitor upgrades impact your sound the most. Chapter 4 delivers your strategic selection guide, matching Purist accuracy with custom character tuning. Chapter 5 establishes critical workbench warnings to safely mitigate failure risks. And finally, Chapters 6 through 9 serve as your ultimate sourcing guides, delivering our premium, physics-backed recommendations for coupling, supply filter, feedback, and decoupling capacitors. Let's dive into the details.
Welcome to Chapter 1. Why does your sound profile change after a component upgrade? On your workbench, an ideal capacitor exists purely as a mathematical abstraction. In theory, its sole duty is pure storage, natively storing and discharging pure electrostatic energy. It demands zero loss, maintaining a flawless 0-ohm ESR and an absolute 0 Henry ESL, alongside absolute phase purity to eliminate harmonic leakage with 0 voltage phase shift. But out in the real world, we confront a harsh reality. Physical structures and raw materials inevitably introduce 4 devastating variables that systematically degrade your amplifier's performance. First, let's dissect ESR, or equivalent series resistance. This internal, pure ohmic resistive loss spikes heavily during thermal stress, drastically choking your charging speed and slew rate while inducing loose, muddy, and sluggish base transients. Second, we encounter ESL, or equivalent series inductance. This parasitic inductance stems directly from your component leads and foil rolls, creating a natural high-frequency block that ruthlessly rolls off and attenuates your ultra-high frequencies while compressing soundstage air and top-end shimmer. Third is dielectric absorption and dissipation. This molecular energy trapping inside the insulation layer distorts high-frequency phase alignment, triggering severe voltage phase shifts that blur stereo imaging focus and crush your 3D soundstage depth. Finally, we face microphonic mechanical resonance. The physical stress of structural foils converts mechanical vibration directly into electrical noise, injecting a parasitic modulation noise floor that chokes background silence and masks vital microscopic details. To master the art of modification, you must look past the capacitance label, analyze these 4 structural parameters, and build with absolute technical precision.
Let's unlock Chapter 2, Material Science Secrets, focusing on standard components versus boutique solutions, Part 1. To master the art of modification, we must first analyze how standard components, found inside generic audio gear, introduce hidden performance bottlenecks. Look at the matrix carefully. A general chemical electrolytic component brings massive native ESR thresholds across low frequencies, combined with a high parasitic ESL driven by its internal foil rolls and unstable dielectric absorption. This chemical structure triggers a highly sensitive mechanical resonance within its thin aluminum casing, resulting in a moderate to high microphonic noise signature that ruthlessly chokes your dynamic speed and muddies your low-end transient definition. Next, while non-inductive general film packages look stable on paper,
Moving toward a standard mylar or polyester configuration introduces a severe high-frequency bottleneck. This standard wrap exhibits elevated ESR spikes in upper registers, leading to noticeable dissipation losses and a distinct high-frequency attenuation that rolls off your top-end air. Finally, your everyday industrial ceramic disc or multi-layer MLCC introduces extreme structural flaws. Despite its microscopic ESL, its piezoelectric behavior injects heavy microphonic noise under structural vibration, paired with an inherently unstable capacitance profile and toxic Class II X7R dielectric absorption that forces hard, analytical grain directly into your high-frequency spectrum. To bridge the gap to high-end audio, you must look past basic capacitance values and identify these standard industrial limits.
Now let's transition to part 2, deep diving into premium boutique solutions. Let's reveal exactly how top-tier manufacturers apply elite material science to eliminate these standard bottlenecks, proving that high-end pricing is backed by absolute technical purpose. To systematically crush ESR barriers, boutique electrolytic components deploy high-purity etched metal foils combined with graphited conductive electrolyte gels, achieving an ultra-low resistance floor that maximizes dynamic weight. To defeat parasitic ESL, boutique film configurations implement complex interwoven non-inductive winding geometries to completely cancel internal magnetic fields, pulling high-frequency phase shifts to absolute zero and expanding holographic depth. Furthermore, premium solutions eliminate harsh dielectric absorption by wrapping high-grade synthetic materials in specialized oil or wax saturation layers, alongside high-density natural silk fiber matrix rings like the legendary ELNA Silmic formula. This fluid chemical barrier smoothly dissolves clinical digital artifacts into pure organic mid-range textures. Lastly, to neutralize structural microphonic noise, these elite boutique components are heavily armored with high-viscosity vibration-dampening fluids, solid resin-encapsulated bodies, and heavy epoxy-dipped outer shells. This locks internal mechanical shifting down to absolute silence, unlocking a pitch-black background contrast and unmatched stereo imaging focus. When you select a premium boutique solution, you are choosing intentional material engineering over standard mass production. Let's advance to Chapter 3. Which capacitor upgrades impact your sound the most? Part 1. To completely eliminate any blind experimentation, we have executed a strict node-by-node capacitor-to-capacitor impact comparison, mapping out clear upgrade priorities across all 4 critical functional stages. Look at the matrix carefully. Sitting at the absolute apex with a flawless score of 10 out of 10 is your C coupling stage. This is your top priority that you must modify first, because it masterfully passes the entire analog audio waveform between amplification stages while completely blocking destructive direct current leakage voltages. This node is absent only in complex DC servo topologies. Tied for a massive score of 9 out of 10 are your C filter and C feedback nodes. Your C filter power supply stage acts as a massive high-priority energy dam, engineered to suppress AC ripple artifacts and feed clean, continuous power to the active rails. Your C feedback stage functions as your high-priority critical precision weapon, which strictly stabilizes loop gain parameters and directly dictates the amplifier circuit's global linearity and distortion response. Finally, earning a powerful score of 8 out of 10 is your C decoupling stage. This highly recommended speed enhancer ruthlessly suppresses localized high-frequency parasitic oscillations and instantly feeds high-speed local IC transient current demands. Analyze this priority blueprint and target your upgrade budget precisely where the physics yields the highest dynamic return.
Now, let's transition to part 2. To be absolutely clear, the functional matrix we just analyzed applies universally to almost every analog amplifier circuit architecture on Earth. To bring this abstract physics directly onto a practical workbench, we are utilizing this classic high-performance LM3886 circuit board design, sourced from Taobao, strictly as a visual case study. No matter what amplifier brand or custom board topology you own, these 4 core target nodes remain identical in physical functionality. Let's trace the locations on our reference model. On the left flank, dominating the layout, sit the massive bulk reservoir filters. These are your C filter nodes, acting as the power supply energy dams. Moving toward the center, right alongside the high-speed silicon tabs, you can spot the localized miniature packages, identifying your C decoupling bypass channels. Positioned closely in front of the active semiconductor stages are the dedicated audio-grade chemical rings, anchoring your crucial C feedback loop stability. And finally, on the right flank, guarding the analog input paths, sits the iconic red WEMA box block, securing your high-priority C coupling node right at the front gate. Remember, this hardware layout serves simply as a physical blueprint to guide your eyes. By understanding these universal functional paths, you can confidently strip away the audio myths and execute your component swaps with laser-focused technical accuracy on any amplifier board you choose to modify.
Welcome to Chapter 4, Strategic Selection Guide, Part 1. To eliminate any blind experimentation, you must first define your modification philosophy. Start right here at the front gate and split your path. On the left flank stands the ideal Purist modder. Your absolute law is zero coloration, upgrading components to the exact same capacitor type while replacing generic factory parts with premium, ultra-precision, low-loss upgrades. On the right flank stands the flavor modder. Your deliberate strategy is artisan character tuning, keeping the same capacitor type but executing a premium upgrade tailored to your specific sonic flavor preferences. Whether you target input waveform tracking, dynamic supply headroom, low-frequency phase linearity, or micro-detail extraction, this master selection map will strictly dictate your component configurations across all 4 critical nodes.
Look at Part 2. Let's execute a direct comparison between Purist and flavor strategies across every primary circuit function. For C coupling, a Purist demands microscopic dielectric absorption and absolute near-zero phase shifts using elite metallized film or Teflon. A flavor modder targets ultra-low microphonic oil damping and smooth, analog second-order harmonics utilizing premium paper and oil or silk fiber chemical formulas. For C filter power reservoirs, a Purist deploys a lightning-fast parallel multi-capacitor bank of ultra-low ESR solid aluminum caps to slash charge delivery latency. A flavor modder demands massive continuous capacitance density and extreme surge ripple current handling using specialized boutique audio electrolytics. For C feedback, the Purist enforces microscopic capacitance drift over time using ultra-precision polystyrene, while the flavor modder installs rich low-frequency damping filters to completely erase phase smear. Finally, for local C decoupling, the Purist slashes high-frequency RF oscillation using solid-state chemical caps or multi-layer ceramics, while the flavor modder masterfully tames sharp high-frequency clinical glare by pairing ultra-low ESR audio caps with premium silver mica bypasses. Select your blueprint, analyze your hardware property, and choose your weapon with absolute precision.
Look at Part 3. Let's establish the mandatory laws for coupling capacitor type selection, dictated strictly by your amplifier's core circuit topology. For vacuum tube amplifiers operating at high voltage rails between 250 to 400 volts, you must strictly deploy paper and oil or premium film technologies. These packages provide ultimate dielectric isolation and near-zero direct current leakage, which is absolutely vital to prevent high voltage leakage from shifting grid bias parameters and destroying your vacuum tubes. For solid-state and integrated circuit topologies, the low-voltage operating rails allow maximum material flexibility. You can confidently deploy film, paper and oil, boutique electrolytics, or wet tantalums to exploit their specific low-impedance harmonic textures. However, be warned, if you swap from a standard factory film package to an electrolytic or tantalum structure, you must multiply the capacitance value by 2 to 4 times to suppress native ESR barriers and fully eliminate low-frequency phase distortion.
Look at Part 4. Let's master your rated voltage selection and uncover the severe acoustic dangers of dielectric underbiasing. For C coupling film and paper and oil packages, strictly upgrade using factory-rated voltage specs, typically between 100 to 400 volts, to keep physical dimensions compact and prevent parasitic ESL inflation. But for all electrolytic and tantalum packages across your C filter, C feedback, and C decoupling nodes, you must strictly enforce a safety threshold of 1.5 to 2 times higher than actual circuit rails. Look at the consequence of overspeccing chemical caps. If you install an overkill high-voltage electrolytic package on a microscopic low-voltage signal path, you trigger incomplete dielectric forming. Low voltage completely stalls the chemical electrolytic burn-in mechanism. This failure severely spikes direct current leakage, destabilizes ESR loops, and causes severe sonic constriction, leaving your mid-range completely constrained, muddy, and lifeless. Keep your voltage safety margins tight, precise, and scientifically optimized.
Look at Part 5. Let's settle the ultimate power supply debate: a single big capacitor versus a parallel capacitor bank. The governing physics here is tau, your circuit's time constant, which equals total system ESR multiplied by capacitance. A single 22,000 microfarad caps brings a native ESR of 12 milliohms and 25 nanohenries of ESL, yielding the slowest time constant of 0.264 milliseconds. This configuration rolls off sharp high-frequency glare and delivers a maximum low-end depth with organic analog fluid weight. Paralleling two 1000-volt grade 10,000 microfarad caps cuts system ESL in half to 10 nanohenries, establishing a balanced 0.220 millisecond transient response. But look at the high-speed alternative. Paralleling five 4700 microfarad caps slashes total system ESR down to a blistering 6 milliohms and drops ESL down to just 4 nanohenries. This commands the fastest time constant of 0.141 milliseconds, delivering a blistering transient attack, deep dynamic macro detail slam, and absolute continuous headroom velocity. However, your engineering execution must strictly match your current system's native character. Never dump a blisteringly fast 5-cap bank into an already clinical, harsh, or bright setup, as it will over-sharpen the high frequencies. Target these speed adjustments precisely to balance and wake up sluggish or muddy systems. Finally, look at Part 6. Upgrading your power supply reservoir capacitance forces massive consequences across your raw hardware infrastructure. When your total filter capacitance expands beyond 20,000 microfarads, you trigger severe inrush current surges during cold power-on sequences. This massive initial velocity will instantly blow standard rectifiers and trip household circuit breakers. To survive this current overshoot, you must upgrade to high-current, heavy-duty bridge rectifiers, or install a dedicated soft-start board to smoothly suppress input current velocity. Furthermore, this continuous, heavy ripple charging current forces your transformer's iron cores straight into magnetic saturation, triggering an aggressive mechanical hum. To execute an ultimate pro solution, upgrade to a higher VA-rated transformer with a massive iron core to expand magnetic flux headroom. For a practical mechanical fix, secure the chassis using high-density isolation damping mounts, or deploy vacuum-varnished toroids to physically eliminate core saturation humming. Never upgrade your filter storage without upgrading your protective infrastructure. Let's advance to Chapter 5, Critical Workbench Warnings and Failure Risk Mitigation. Before you open your sourcing guide, you must respect these 6 mandatory safety thresholds to prevent catastrophic component failures. First, polarity orientation. Reversing the positive and negative orientations on polar electrolytic or tantalum caps will immediately destroy the components. Rigorously inspect PCB markings and casing stripes before soldering, and deploy non-polar variants like the Nichicon Muse ES on AC signal paths to eliminate polarity risks. Second, voltage margins. Operating near or slightly above maximum rated voltage leads to dielectric breakdown and explosive component failure. Strictly enforce a minimum safety threshold of 1.5 to 2 times higher than actual circuit rails, and always account for AC audio peak-to-peak voltage swings. Third, tantalum capacitors. Tantalum packages possess absolute zero tolerance for current spikes, overshoots, or reverse biasing, causing rapid, catastrophic short-circuit fire hazards. Always enforce an overkill safety margin of 2 to 3 times. Ensure perfect polarity orientation and strictly avoid high ripple current nodes. Fourth, space limitations.
Boutique or high-voltage capacitors feature massive physical footprints that physically conflict with standard PCB component spacing. Always measure your physical lead pitch and internal chassis volume clearance before sourcing, and prepare alternative off-board lead wire extensions if the chassis space is tight. Fifth, thermal stress. Extended soldering dwell time transfers extreme heat straight into the capacitor core, melting film sheets or cracking delicate silver mica dielectrics. Limit your soldering iron dwell time to a strict 2 to 3 second threshold, and clamp a needle nose plier onto the component lead as a physical heat sink during your soldering operations. Finally, PCB fitment. Boutique or heavy-duty snap-in leads feature oversized diameters that physically rupture standard PCB-plated through holes or vias. Never force or twist heavy leads into tight vias under any circumstances. Utilize a micro drill to safely enlarge PCB via geometries or fabricate flexible wire extensions. Memorize these 6 Workbench laws to secure absolute reliability before executing your component swaps.
Let's advance to Chapter 6, Recommended Coupling Capacitors, Part 1. When selecting a boutique audio-grade film capacitor for your analog signal path, we must focus strictly on the universal coupling range, typically between 0.1 to 10 microfarads, where performance and market value intersect perfectly. Look at our selection matrix. First, the WEMA MKP10. This metallized polypropylene design serves as our absolute budget workhorse, delivering an ultra-neutral, laser-sharp analytical accuracy with a crisp, high-frequency edge at a highly accessible price point. Second, the Mundorf MCAP Evo Oil. Engineered with advanced polypropylene in an oil mist, this white casing minimal package injects a window-like transparency with an added organic, liquid smoothness, gracefully expanding your 3D soundstage width. Third, the legendary Mundorf MCAP Supreme Classic. Utilizing a heavy black casing interwoven non-inductive winding structure, this reference component achieves an absolute zero-phase distortion floor, yielding a laser-sharp instrument focus and massive holographic soundstage depth. Fourth, from Denmark, the Janssen Audio Superior Z-Cap. This ultra-tight metallized polypropylene design is exceptionally neutral, pulling out superb micro-detail extraction from a dead-silent background with absolutely no added coloration. Finally, the Elite V-Cap ODM, or oil-damped metallized polypropylene. This flagship miniature masterpiece delivers a blisteringly fast transient attack with immense continuous air, packaging ultimate mechanical precision into a microscopic footprint. Analyze these sonic profile characters, match them to your acoustic target, and select the ideal film formula for your next modification.
Let's advance to Part 2, focusing on premium PIO and Paper-Wax capacitors. In the high-voltage, high-impedance universe of vacuum tube amplifier circuit topologies, these natural organic dielectrics serve as the ultimate coupling choice. Here, we shift our focus down to the highly critical fractional microfarad spectrum, typically between 0.01 to 0.47 microfarads, where these classic structures yield maximum dynamic return without risking motorboating oscillation or grid blocking distortion. Look at the matrix. First, the Jupiter copper foil paper and wax. By replacing fluid oil with pure beeswax impregnated paper, this American artisan masterpiece masterfully damps internal mechanical microphonic noise down to absolute silence. It delivers a heavily emotional, organic liquid presentation with an unmatched vocal thickness and a breathtaking mid-range bloom. Second, the legendary Jensen paper and oil with aluminum foil. Sourced from Denmark, this iconic vintage king injects a silky, sweet, and gracefully rounded top-end air shimmer, masterfully bleeding off harsh digital artifacts while preserving profound analog warmth and spatial depth. Finally, the Russian K40Y9NOS military package. This aluminum foil and paper and oil tank functions as an extremely cost-effective analog damping weapon, delivering a dense, heavy vocal weight with a smooth, high-frequency roll-off at an unbeatable surplus rate. If your acoustic target demands pure, uncompromised analog musicality, these natural core formulas are your ultimate solution.
Let's close Chapter 6 with Part 3, exploring audio-grade electrolytic and Mil-Spec tantalum capacitors. When deploying chemical formulas as coupling nodes on low-voltage operating input rails, you must strictly implement our strategic safety law. Keep your factory-rated voltage tight, ideally between 25 to 50 volts maximum, to ensure incomplete dielectric forming never stalls your burn-in mechanism. Look at our final selection matrix. First, the ELNA Silmic 2 RFS series. Utilizing a specialized natural silk fiber core, this legendary component stands as our primary warmth weapon, delivering rich, highly liquid vocal textures, while smoothly dissolving harsh, high-frequency digital glare into pure musicality. Second, the Nichicon Muse ES bipolar. This specialized non-polar chemical package is our reference standard for low-frequency phase alignment, establishing a dead-silent noise floor with a solid, uncompressed low-bass punch. Third, the ultra-premium Audio Note Case-I. Engineered with elite Rubicon graphite gate formulas, this holy grail component delivers unrivaled continuous energy headroom, transferring breathtaking analog weight, density, and immense wide dynamic slam. Fourth, the Sprague 150D solid tantalum. Utilizing a solid tantalum sintered pellet structure, this studio legend injects blisteringly fast transient speed, paired with exceptionally tight, laser-focused structural imaging. Finally, the pinnacle of military hardware, the Sprague 109D wet tantalum. Armored in a hermetic acid-liquid Mil-Spec casing, this elite package seals direct current leakage down to absolute near zero, with supreme thermal stability, introducing an ultra-liquid, deeply emotional mid-range with sweet, highly refined highs. Match these chemical blueprints precisely to your circuit topography, select your rated voltage with strict technical precision, and unlock the absolute performance threshold of your amplifier hardware.
Let's advance to Chapter 7, Recommended Supply Filter Capacitors, Part 1. When engineering your primary power supply reservoir bank, we focus strictly on the massive snap-in performance spectrum, ranging from 4,700 to 22,000 microfarads. In this high-priority domain, these heavy-duty component packages function as your master energy dams, engineered to suppress alternating current ripple artifacts and inject raw, continuous current velocity. Look at our selection matrix. First, the Nichicon GoldTune KG series. Serving as the gold audio standard and our reliable modders benchmark, this advanced etched foil design injects a rich, organic analog weight with an exceptionally thick, deep low-end authority and liquid mid-range presence. Second, the legendary Nichicon Super Through KG series. Armored with elite dual-pin heavy foil geometry, this ultimate holy grail snap-in capacitor delivers an absolute window-like transparency with a blisteringly fast dynamic slam and dead-silent background contrast for laser-focused bass textures. Third, the German-engineered Mundorf M-Lytic AG audio grade. Implemented with a specialized high-speed, low-inductance formula, this premium package ruthlessly slices through power line ripple noise to deliver an incredible transient response speed with a tight, highly tactile low-end punch and wide European spatial airy dimension. Fourth, the Cornell Dubilier CDE 3080LX. This industrial heavy-duty electrolytic titan delivers raw, muscle car dynamic authority, packing deep, uncompressed continuous power headroom with zero dynamic sagging into a highly cost-effective structure. Finally, the ultimate industrial speed demon, the EPCOS TDK B43504. This high-reliability, industrial-grade masterpiece utilizes an ultra-low ESR formula to deliver cold, pure clinical precision with absolute linear, uncolored behavior. It masterfully tightens flabby, sluggish bass into highly controlled, fast-pulsing rhythmic hits. For equivalent setups, look for the Nippon Chemicon LXG or Rubicon MXG alternatives. Secure your protective infrastructure, match these filter storage formulas to your power rails, and feed your active semiconductor circuits with absolute current stability. Let's close Chapter 7 with Part 2, deep diving into premium lead and radial C filters, engineered specifically for low-voltage, low-current preamplifier and operational amplifier circuit rails. In this sensitive domain, we focus strictly on the compact capacitor footprint,
typically between 10 to 1,000 microfarads, where minimizing structural impedance and ripple noise is critical to secure a pristine signal baseline. Look at our selection matrix. First, the Nichicon Feingold FG series. Serving as our sweet musical standard, this premium audio-grade chemical design injects a warm, velvety analog sweetness with a rich, seductive vocal body, masterfully softening harsh, high-frequency digital artifacts into pure liquid flow. Second, the ELNA Silmic 2 RFS series. Backed by a natural silk fiber damped chemical matrix, this soulful warmth king delivers a breathtakingly airy and emotional vocal presentation, utilizing elite mechanical microphonic dampening to round off edge artifacts gracefully.
Third, the Panasonic FR and FM series. Functioning as our dead silent budget tool, this ultra-low ESR industrial formula delivers a blisteringly fast transient speed with supreme, uncolored neutrality, slashing powerline ripples down to a dead silent noise floor level. Fourth, the ultra-premium Audio Note Kaisei Radial. Formulated with elite Rubicon graphite gate technology, this holy grail capacitor transfers a breathtaking inner density, weight, and continuous energy velocity headroom, breathing high-end analog musicality straight into your low-voltage nodes. Finally, the Sanyo Suncon WG series. This solid-state high-conductive polymer acts as an extreme speed enhancer, shattering near-zero high-frequency ESR barriers to deliver pin-sharp micro-detail extraction with an ultra-dynamic top-end air shimmer. Match these compact blueprints precisely to your preamp circuit stages. Choose your rated voltage using our strict 1.5 to 2 times multiplier law, and secure flawless sonic purity right at the foundation of your power supply.
Let's advance to Chapter 8, Recommended Feedback Capacitors. Inside your global loop feedback topology, this specific capacitor functions as your critical precision weapon, strictly stabilizing loop gain parameters and directly dictating the circuit's global linearity. To secure perfect low-frequency phase alignment without risking bass attenuation, we focus on the dedicated feedback spectrum, typically between 22 to 100 microfarads. For your rated voltage selection, remember our safety law. Maintain a tight 1.5 to 2 times multiplier for solid-state layouts, but immediately scale up to a heavy 250 volts or higher for high-voltage vacuum tube architectures. Look at our selection matrix. First, the Nichicon Muse ES bipolar nonpolar series. Serving as the absolute standard for feedback tuning, this specialized nonpolar chemical package completely eliminates directional polarization distortion, delivering a dead-silent noise floor contrast with a deep, uncompressed, and razor-sharp low-bass focus. Second, the ELNA Silmic 2 RFS series. This natural silk fiber-damped electrolytic stands as our primary vocal weapon, injecting immense analog emotional liquidity and natural organic weight into the mid-bass, while masterfully rounding off harsh high-frequency silicon glare to preserve a soulful mid-range bloom. Finally, the ultra-premium Audio Note Kaisei Radial, powered by the elite Rubicon formula. Implementing non-antisymmetric graphite gate specifications, this ultimate holy grail design commands an unmatched continuous energy headroom velocity, transferring breathtaking holographic density, raw power, and massive 3D soundstage depth with thunderous dynamic low-end macro detail slam. Lock in your rated voltage margins, analyze your system's native character, and deploy the ideal feedback formula to establish absolute fidelity across your amplifier's return loop.
Let's execute our final curtain call for the Capacitor Masterclass with Chapter 9, Recommended Decoupling Capacitors, Part 2. Positioned directly per-shit core active semiconductor and integrated circuit power pins, these localized decoupling units function as your high-speed miniature transient reservoirs. To ruthlessly shunt megahertz radio frequency interference directly down to zero floor while avoiding parasitic ESL inflation, we target the compact micro-footprint spectrum, typically between 100 to 220 microfarads,
alongside a dedicated 0.1 microfarad film bypass. For your rated voltage selection, remember our master design law. Strictly enforce a tight 1.5 to 2 times safety factor to keep the physical casing slender and maximize transient discharge speed.
Look at our final selection matrix. First, the Sanyo Panasonic OSCON, SVP, or SEPC series. Standing as the lightning transient king, this solid-state conductive polymer completely shatters high-frequency ESR and ESL barriers, delivering a blisteringly fast speed, razor-sharp edge definition, and extreme micro-detail extraction.
Second, the Nichicon FW series audio-grade standard. This premium fine chemical liquid package delivers a superb electroacoustic balance, masterfully sharpening upper register transient speed while retaining a rich, natural vocal body and cleaning continuous line ripples into a deeply liquid, uncolored sonic texture. Third, our ultimate anti-glare weapon, the ELNA Silmic 2 RFS series. Anchored by a natural silk fiber damped electrolytic matrix, it masterfully damps and dissolves sharp, clinical, fatiguing digital glare, injecting rich analog weight, density, and a deeply emotional mid-range bloom directly into the active local voltage nodes. Finally, the WEMA MKS2 or MKP2 0.1 microfarad miniature film. Being natively free from chemical aging, it is the absolute artisan choice for parallel bypass underneath your PCB trace layout, ruthlessly trapping and shunting stray high-frequency noise interference out of your circuit.
With our master blueprints complete, secure your voltage margins, trust the physics of material engineering, and execute your component swaps with absolute laser-focused technical precision.
That wraps up our guide. Keep your voltage safety margins right. Choose the capacitor type that matches your system's character, and execute your component swaps with clean technical accuracy. If this practical breakdown helped your DIY knowledge, please subscribe to the channel. Thanks for watching Rty DIY Audio. Happy building, and see you in the next video.